Here's a video that shows you how to calculate torques exerted by various forces. It's based on problem number 56 from the end of chapter 10. So before watching this video, you might want to dredge out that problem and take a look at it, at least so you can get an idea of what the situation describes. So basically, it's about a large beam that's supported by a hinge on a wall. So I haven't drawn the wall here, but there's a beam supported by a hinge. And so that it doesn't fall down because of gravity, there's a cable that's attached to the end of the hinge up here that pulls the top of the hinge up. So basically the cable is holding the beam up and gravity is trying to pull it down. There's clearly some forces exerted at the hinge here, probably to hold the beam up and push it this way away from the wall. But for this example, I'm not too interested in those forces. Really, what I'd like to do is to solve a variant of this problem. I just wanted you to be able to have the diagram to look at. Here's what I want to make up. I want to set the tension in the cable equal to 1,000 newtons. In the problem, that's the breaking strength of the cable for what that's worth. And also in the problem, the length of the beam, you're told, is 1.2 meters. But I'll also go ahead and tell you the mass of the beam. The mass of the beam is 118 kilograms. So that's pretty heavy. And what I would like to calculate is, very specifically, the net torque about the origin, this point right here, the hinge. So I want to know what's the net torque exerted by the forces on the beam about that origin right there. Whenever you calculate torques, you need to specify a point or an origin or an axis of rotation about which to calculate the torques. So here's what we have. We have the beam, and I've drawn here a vector to represent the tension force, which again is 1,000 newtons exerted at the very end of the beam. Where am I going to put the weight force? So gravity acts everywhere on all the bits and pieces of this mass. But where is the single point from a mechanics perspective we could concentrate all of that mass to have the same effect? Well, if you haven't guessed already, it's at the center of mass. That's the reason why in a previous chapter we learned about calculating center of mass. So I'm going to go ahead and draw a weight vector here, approximately at the center. And if we wanted to calculate what the weight vector was, we'd use m times g. So I want to calculate the torque exerted by the tension force on the beam about this origin, and I want to calculate the torque by the weight force on the beam about this origin. So we'll calculate two torques and add them together to get the net torque. So which one would you like to do first? For me, I think I'm going to take a look at the tension force. So how am I going to calculate the torque due to that tension force? Well, as I tried to illustrate in a different video and as you can read about in the book, the only way to reliably go about determining torques is to determine the so-called moment arm or lever arm. And so the method is like this. You extend the line that contains the force equally in all directions, and that's called the line of action. And then you look for the perpendicular distance between the line of action and the origin. So pretty clearly, that's this distance right here that we need. So that's the lever arm we need in order to calculate the torque due to the tension force T. So how far is that from the origin to the line that contains that force, which in this case is also the cable? It's not too hard to figure out. The angle that the beam is elevated in the problem is 30 degrees, but you can see by, if you remember alternate interior angles, that's also 30 degrees. So it's pretty clear that we have the hypotenuse, which is the length L, and in order to get the lever arm or the moment arm for the tension force, we need the opposite side. So the opposite side is the sine side of this triangle if you want to think about it like this. So I need the tension force times the moment arm for that tension force, but that's going to be the length of the beam times the sine of 30 degrees. So that's going to be T times L times the sine of 30 degrees. So that's great. You can plug those numbers into your calculator as well as me. You need 1,000 newtons times 1.2 meters times the sine of 30 degrees, which happens to be a half, and I'm pretty sure you're going to get exactly 600 newton meters. So if we're doing a 3 sig fig problem, then that 0 is significant, but if we're doing a 2 sig fig problem, this 0 isn't, but this one is. Now what's the direction of this torque? Well, if it were left only to that tension force, that would tend to rotate the beam up in a counterclockwise direction. So I'm going to remind myself that that's a counterclockwise torque by putting a plus sign, because we're going to define the counterclockwise direction to be plus. Great. Now let's figure out the torque due to the weight force. Same thing as before. We're going to need the magnitude of the force, mg, and we're going to need the moment arm or the lever arm to that weight force. So let's see what that one is. Well, I'll extend the weight force in all directions. You can see I don't have to extend it really far because this right here is the distance that I need. That's the moment arm for the weight vector, from the origin horizontally to the weight vector, because again, they got to meet at a right angle. So what do I have here? Well, from here to the place where the center of mass is, if it's a uniform beam, that's half the length of the beam. And I see a little triangle here, where I have the hypotenuse, half the length of the beam, the angle, and to get the moment arm for the weight force, I need the cosine side of that. So to me that looks like the weight vector times half the length of the beam times the cosine of 30 degrees. So you can calculate that out as well as I can. And to 3 sig figs, I think I end up with like 601 Newton meters. Now what about the direction? Well, this force would pull the beam down, so that is a clockwise rotation, and we're going to make that minus. So then if I want to find the net torque, I just got to add these up. So 600 plus, 600 minus. In this particular case, I get a really nice 0 to 1 or to 2 sig figs. 3 sig figs, not a 0, but this is a 2 sig fig problem. So I'm confident at saying for the numbers I picked here, the net torque happens to be 0. So this process of drawing forces on objects and then using the line of action to calculate the moment arm for each of the forces is the most reliable way to calculate torques.